Okay, hello there. So we're going to talk about uniform circular motion. Any object moving in a circle at a constant speed is undergoing uniform circular motion. For an object to stay on a circular path, it must experience an acceleration toward the center of the circle. Now that's a little bit of a counterintuitive thing, right? You go around a curve, you feel like you're in a car and you feel like you're being thrown to the outside of the car, right? So the outside of the circle. But think about the force that results when you lean up against the door or are shoved up against the door, okay? That force is a normal force, and it's not pressing, you're pressing on the door outward on the circle, but the circle, or rather the door, is pressing you inward toward the center of the circle. So if this is you going through some little part of a circle on a curve in a car, well, then your velocity is changing direction. Sure, it's not changing magnitude, right? That's something we say here. And the constant speed is the uniform part of circular motion, okay, or uniform circular motion. But your direction is changing. If you change your velocity, right, change your velocity, doesn't matter whether it's just direction, you have an acceleration, okay? And the question is, what kind of acceleration must that be? Well, it must be supplied by some force, you going around the curve in a car, and then you pressing up against the door, and the door pressing back on you. Well, then that force is partially responsible for giving you this center-facing acceleration, okay? But that acceleration must be towards the center. So if we were to draw it in here, it would be perpendicular to the velocities there, okay? And we call that centripetal acceleration. And we'll talk a little bit more about it. But first, a little more on why it must be in that direction. Take, for example, another two spots on the circle. Let me see if I can grab a different color here. And we go from maybe that point to that point. And if we're going this is the same object, so our velocity starts out going this direction, and it ends up over this direction. Okay, so we're going through 90-degree turn in these 2 points. Okay, well, we need an acceleration that's going to take this velocity that's in sort of the downward negative y direction, okay, and change it into a velocity that's going completely in the positive x direction. Okay, so that means that whatever acceleration we've got, well, it better have a little component in the positive y, and it better have a component in the positive x. And if we think about that for a moment, well, the size of velocity that it needs to reduce to 0, right? Because down here, at position 2, there's no y component to it. So we need to take that y velocity and take it to 0, and we need to take the 0x velocity at position 1 and turn it into v, right? Whatever that speed is, okay? And to get that to happen, you need an acceleration that's in this direction, right? This is the acceleration that you need for that to happen, the average acceleration. And if you think about that, average acceleration is exactly perpendicular during this whole transition from point 1 to point 2 to that thing. Now, that's an average acceleration. This doesn't prove that it has to be instantaneously exactly towards the center of the circle, right? We're blurring out some details here. But I'm just trying to convince you that whatever acceleration you have for an object going around a circle like this, you need it towards the center of the circle if you're going to be bending the velocity direction in the way that traces out a circle, okay? So, if we add that to our diagram, we have this a sub c always radially inward towards the center of the circle. And this can be a lot of different objects going around the circle. It can be the car going around a curve. It can be a ball on the end of a string. It can be some water in a bucket that you're whirling over your head. It can be a planet going around a sun. It can be all kinds of things. As long as you're going in a circle and you're going at constant speed, then all of the provisions that we're about to lay out are going to apply to you. So what is the centripetal acceleration? We must be able to calculate it in some way, and indeed we can. Centripetal acceleration, so centripetal, that's this right here, okay? It translates to center facing. I think the original root is Greek or something like that. This equation gives the magnitude of that acceleration. It's related to the object's speed squared, so the magnitude of its velocity squared right here, and it's related to the radius of a circular path. Okay. So to examine whether that makes sense to us, let's consider a couple of situations, right? Well, as speed goes down, then there's a less rapid change in velocity direction, and so we shouldn't need quite as much acceleration. I think that tracks. And if the radius of the circle goes down, right, so we're going around a tighter circle, then we have a more rapid change in velocity direction, and we would expect there to be more acceleration needed. And if you're thinking about that car example that I brought up initially, well, think about going at 60 miles an hour around a curve in like a freeway, which tend to be quite gradual. So R, in that case, would be large, and V would be, 65 miles per hour, say, but some constant value. Now compare that to not being on the freeway, but you going that same speed, okay, going like, I don't know, around a tight exit ramp. Like you get off the highway and it has one of those signs that says, you should be going off of this exit ramp at 25 miles an hour, but you decide, no, that's not for me. I'm going to keep going 65 miles per hour. Well, now your radius is relatively small, okay? And you know that you need a whole lot of grip with your tires, and you're really going to be flung to the outside of that circle, and so that door of yours is going to be pushing back on you and giving you this very large necessary centripetal acceleration, right? So small radius of a circular path with a relatively high velocity, then you would expect a relatively high centripetal acceleration, okay, because you're going around a very tight turn, a small radius. Now, if you go back to the previous situation where you're on a freeway and you're at a large radius curve, well then the change in direction of that velocity, even though the velocity is relatively big, the change in direction there is pretty gradual compared to the other case, okay? And you feel it, right? You know if you're going around a curve on a road, but you're not going to be flung into the door. The friction between your legs and the seat is going to be enough to keep you in place and make you nice and comfy. Okay, so there's a couple of other examples you could think of conceptually to convince yourself that the form of this equation is reasonable. And in a future video, we'll look a little bit closer at exactly how this particular form comes about, like why it's v squared, for instance. I mean, other than the fact that it makes the units work out, okay? So that's where we're going to head next, okay? And I'll see you then.